Alright, this is Integrated Math 3, and this is your fourth lesson in statistics. It's the final lesson in this unit. It's 1.04 and it's on z-score. So z-score is simply how many standard deviations a particular value is above or below the mean. That's very simply what it is. So you calculate z-scores in the following situations. Comment on how average or unusual they are. Well, let's first of all have the formula. So the z-score is equal to your data value, the one that you're interested in knowing about, minus the mean, and then you divide that by the standard deviation. Okay, so the data value, the mean, and the standard deviation. It's just, that's the only formula in this entire unit. Okay, so let's go ahead. Number one, the number of red loops in a box of Tutti Fruttios is normally distributed with a mean of 800 loops and a standard deviation of 120. Tony bought a new box, opened it, and counted 1,243 red loops. It didn't really matter because all the colors are the same flavor anyway. Okay, well anyway, so what do we have here? We have a mean mu of 800 loops, and we have a standard deviation sigma of 120, and then we have the value that he received. What he counted was 1,243. So we just simply plug into the formula. Okay, so you're going to subtract the two numbers on the top, and you're going to get 443 over 120. And you should use a calculator for that. And that's going to give you 3.7 standard deviations above the mean. Well, as you saw in all the previous assignments, we pretty much considered 3 standard deviations to be way out on the edge. It's like 99% of the values, more than 99%. So this is really, really unusual that he would get that many when the mean is 800 and the standard deviation is 120. So if you just want to put it in one word, unusually high number. One phrase. Okay. Next. The weight of house cats is normally distributed with a mean of 10 pounds and a standard deviation of 2.1. My cat Big Boy weighs 6 pounds. Okay, so I want to know where Big Boy is on that scale. So mean 10 pounds. I'm not writing units of measure. I should, to be proper, should be pounds there. Standard deviation is 2.1. And Big Boy is 6 pounds. So that's X. That's the data value we're interested in. And I'm going to just say 4 divided by, it looks like about 2, is going to equal -2 standard deviations. It'll be a little bit less than that because that's a little bit more than 2. So it's -2 standard deviations below the mean. So Big Boy is really not all that big. Big Boy's, I don't know, Big Boy's not big compared to the mean value of cats. 2 standard deviations below, that means that 97.5% of all cats are heavier or bigger than Big Boy. How did I get that? Well, we do a meter here. We said if you're -2 standard deviations, 50% of the cats are up here, and 47.5% of the cats are between the mean or the median and -2 standard deviations. You add those together, you get 97.5% of all cats are heavier than where that cat came in. Okay, let's keep going. The lifetime of battery is normally distributed with a mean life of 40. Let's just go ahead and write this as we read it. Mean of 40. hours and a standard deviation of 1.2. hours, and I just bought a battery that died after 20 hours. Okay, so X is 20. Okay, and that gives you negative 16.7. And I mean, that's just way. I mean, we were talking about 3 standard deviation below the mean as being pretty much everything as low as you could get, and this is negative 16. So this was just clearly a defective battery. It shouldn't even have been. It shouldn't even have made it past the inspection. Or something damaged the battery in some way, but that's way below what you should at all expect, given that the mean is 40. Okay, number 4. The amount that a human fingernail grows in a year is normally distributed with a mean of 3.5 and a standard deviation of 0.63. These are in centimeters. My neighbor's fingernail grew all year without breaking, and it is 4.6 centimeters longer than it was at the beginning of the year. Okay, so let's do Z value. Okay, and that gives us 1.7 centimeters, or excuse me, 1.7 standard deviations. So, if it was 2 standard deviations, it would be longer than 97.5% of all fingernails. If it was 1 standard deviation, it would be longer than 84. So we're somewhere in between those two, so it's probably longer than about a little over 90% of all fingernails, 1.7, just making an estimate there. All right, so that's well above average. Okay, my son was digging in the garden and found an earthworm that was 35 centimeters long, so that's the X. The length of earthworms is normally distributed around a mean of 14, so the mean. And the standard deviation, 5.3. And that earthworm was 35. Okay, so again, we're getting these, what are called outliers. They're just way out of the norm here. So Z equals and we're looking at, in round numbers, 4 standard deviations, and that's way outside. 3 standard deviations, again, is 99. It's greater than 99.7%, so this is way above that. So this is definitely what would be called an outlier. All right, keep going. And it says the mean length of a human pregnancy is 268 days. With a standard deviation of 16. And let's see, somebody just had a premature delivery at 2:45. And you'll notice this gets pretty repetitive. That's the actual value. The mean is this. And the standard deviation sigma. And that gives you negative 1.4 standard deviations. Below the mean. Okay. So 16% of all pregnancies would be below 1 standard deviation. This is 1.4, so this is down around the lower 9 or 10% of all pregnancies would be that far below the mean. So in other words, she had her baby pretty early compared to others. About 90% of pregnancies last longer than this number, and about 10% last shorter than that. It's about 90%. Okay, so that's again, that's just from looking at a lot of standard deviations and seeing how many percent that would be. Okay, there you go. But that's the answer, is negative 1.4. Okay, let's keep going. IQ scores for young adults, famous IQ test. The mean is 110. And a standard deviation is 25. And then we have a person who has an IQ of 170. Okay, and that's going to equal 2.4. Standard deviations above the mean. So that means that person is somewhere between 95 and 99.7. So that person's above about 97 or 98% of all people in terms of the IQ score. Again, just go back to some of the percentages and some of the earlier assignments, and 2 standard deviations is 95%. They're above. If it was 3 standard deviations, they'd be above 99.7. So 2.4 is somewhere in between 2 and 3. So we're going to say 97%, 98%, somewhere in that. Okay, let's keep going. They seem to want to ask you a lot of these questions here. Okay, the Army measured head sizes among males, found that distributed pretty close to a mean of 22.8. And you notice I'm rushing through these questions. You're really just looking for the numbers here. Standard deviation of 1.1. And let's see. Little Joe had a head size of 20.6. Okay. So little Joe's head was negative 2 standard deviations below the average, which means his head was smaller than 97.5% of all heads. Because he was negative 2, so you take the 50% that's above. You take the 50% on the left side of the chart. Okay, and he's right here. So this is 47.5, and he's right here. Here's little Joe's head right there. So 50 minus 47.5 is 2.5. So there's only 2.5% of all people that have a head smaller than little Joe. Okay, that's one way to look at it. All right, there he is. Okay, all right, keep going. Okay, now they're giving us so for 9 through 11, we're going to use this information. The population of NBA players is normally distributed with a mean of 6.7 or 6 feet 7 inches. And a standard deviation of 3.9 inches. Greg is considered unusually tall for his high school at 6.3. So here's the thing about this one that just complicates it a little. So it's 6 feet, that's the single tick mark. 7 inches, that's 2 tick marks. You got to convert it into inches. Here you got feet and inches, and it's not a base 10 system. As you know, there's 12 inches in a foot. So it's not a base 10 system. So you can't put 6.7 in other words. So you got to figure it out. So what you do is this 6 times 12, that's how many inches in a foot, plus 7. So 6 times 12 is 72, plus 7 is 79 inches. Okay. Now everything is in inches, so you can now work the problem. So mu, we're going to say, is 79 inches. Okay, the standard deviation is 3.9 inches. And Greg is 6 foot 3 inches, so that's 6 times 12. This is Greg, plus 3 more inches. And that equals 75 inches. Again, what we had to do that because feet and inches are not a decimal base 10 system. So you can't say 6.7. It's 6 times 12 plus 7 more inches. These over here. Okay, so now we can go ahead and work the problem here. And negative 4 over 3.9 is close enough to 4, so we can just say that it's negative 1. So it's negative 1 standard deviation. Okay, so that means that 50%, so here's 1 standard deviation. We know that's 34%. We know this is 50%. So 50 minus 34 over here is 16%. This minus this gives you this. 16%. So that means Greg is taller than 16% of the players in the NBA. Okay. What percent are shorter than Greg? And there we got. So 16% are shorter than Greg. Okay. All right. How tall would Greg have to be in order to be in the top 2.5% of NBA players? Okay, so 2.5%, let's go ahead and draw the diagram here. And let's remember what 2.5% is. So this is 34%. 2 standard deviations takes you out to 47.5% because you add that to the other side and it's 95%. So out here is 2.5%. So this is 2.5%. So basically it's 2 standard deviations away. In other words, what height would he have to be 2 standard deviations away? So this one you have to work the formula a little bit differently. So you want him to be, he wants to be 2 standard deviations away because that'll make him shorter than only 2.5% of the NBA players. Okay, so that would put him in the top 2.5%. So the Z value here is going to be 2. Here's the formula again. So let's write the formula. Okay, is X minus mean over standard deviation. Okay. All right, so he wants to be 2 standard deviations away. Okay, let's just adjust this a little bit. So he wants to be 2 standard deviations away. That's what Z is. It's how many standard deviations he is. So then we need to know what value X, how tall, that's how tall he would have to be, minus the mean. And the mean is 79 over 1 standard deviation, and that's 3.9. So you're going to have to go to work, do a little algebra on this. So let's talk about our algebra skills here. You need to get this by itself. That means you have to get rid of this and this. Which one do you do first? Well, you do this one. You multiply both sides. You always get rid of a denominator first when you have something like this, by 3.9. That means you're going to multiply this side by 3.9. Anything you do to one side, you do to the other. That cancel. Down here we have 2.3.9. 2 times 3.9 is 7.8. Equals X minus 79. Okay, so we're going to add 79 to both sides. These cancel, and 7.8 plus 79 is going to be 86.8. So X is going to equal, just added these two, do it on a calculator, 86.8 inches if he's going to be taller, but except for all but 2.5%. So he's taller than 97.5% of the NBA players. And if you converted that to feet, that would be 7 feet 2.8 inches. 7 feet 2. Let's just call it 3. Let's just round it up to 3. 7 feet 3 inches. Okay. So he's a center. All right, and that's how you do that one. That one took a little algebra to do that. So in this case, you knew what he wanted to be, what we were looking for. You knew what the mean and the standard deviation were, so you had to figure out what number of inches does that make him. Okay, we got a new problem set. The average height of boys at Greg's school is 5.9 with a standard deviation of 2. Assume the population is normally distributed. Okay, so what percent of students in the school are shorter than Greg? First of all, we got to convert 5 feet 9 into inches. So 5 feet times 12 inches plus 9 inches. So PEMDAS says you do that first. You get 60 plus 9. So he's 69 inches tall. So X equals 69 inches. Okay, my bad. My bad, and whoever wrote this question's bad. So that's actually the mean. The mean is 69 inches. It doesn't say how tall Greg is. You got to know that if you're going to answer that question. Let's just say he's 5'11". So X equals 5'11". So that's going to be 71 inches. And then the standard deviation is 2. Okay, so we're trying to find Z. Okay, so I picked a nice number for you for standard deviation for his height, because it makes the standard deviation exactly one. So he's 1 standard deviation above the mean, so we draw our curve here. So we know that 50% of the students are below the mean. That's right there. That's 50%. And then 1 standard deviation is a number you should know by now. It's 34%. So he's taller than 50 plus 34. So he's taller than 84% of the boys at his school. Okay. All right. What percent of students... What percent of students are between 5'5" and 5'11"? Okay, so let's do what we did before. The mean is 69. And I'm going to do these conversions real quick. If you go 2 standard deviations above that, you get to 5'11". That's going to be 71. Again, 2 more inches is another standard deviation. That's 73. And then 75. So let me label those. That's 3 standard deviations, 2. Okay, there we go. So there's the mean, and there's the various numbers of standard deviation. So students between 5'5", so 5'5", and 5'11". Okay, so let's draw our curve. This one's a little unusual from some of the earlier questions. So this is 69 inches. 1 standard deviation above is 71 inches. That's 5'11". I'll write it in both. 5 feet 11 inches. 2 standard deviations is 6 feet 1 inch. And that's 2 standard deviations. So that's 73 inches. Okay, going in the other direction. And that's going to be 69, 67 inches. So that's 5 feet 7 inches. And the next one, 2 standard deviations, is going to be 5 feet 5 inches. And that's 65 inches. So let's stop right there, because that's what they're asking about. 5'5" and 5'11", this and this. So it says, what percent of students are between 5'5" and 5'11"? So 5'5" is 2 standard deviations below the mean. and that's going to be 47.5%, half of 95. And then 511 is 1 standard deviation above the mean, and that's the 34%. So they gave you 2 standard deviations to the left, but only 1 to the right. That's fine. They wanted to know those 2 values. So that's going to be 47, 77, 81. So it's going to be 81. I'm just going to add them over here. 47.5. That's the 5 in that direction, plus 34%. And that's going to be 81.5. Okay, I'm going to skip 14 and 15. I just feel like there's a flaw in that question, and I'm not going to do it. So you can skip that too. Okay, here's a lot of words here, so let's read them. College admissions officers evaluate hundreds of applications from students that want to attend their school. Many of them have good grades, have participated in school activities, have done service within their communities, and all kinds of other attributes that would make them great candidates for attending the college they represent. Applicants' scores on the college entrance examination is considered carefully. Some students take the ACT and some students take the SAT. A college admissions officer has to make a final decision on 2 applicants. They are both wonderful students with the very same GPA and class rankings. It all comes down to their test scores. Student A took the ACT and received a score of 29 in mathematics. Student B took the SAT and received a score of 680 in mathematics. Both tests are designed to be normally distributed. A perfect ACT score is 36. The ACT mathematics section has a mean of 21 and a standard deviation of 5.3. A perfect SAT is 800. The SAT mathematics section has a mean of 516 and a standard deviation of 116. Based on their test scores, which student should be chosen? Okay, so who did better on the math? All right, so student A took the ACT. So the perfect score doesn't matter. It's the mean and the standard deviation. So for A, the mean for that test is 21. Standard deviation is 5.3. And the X value, what that student actually received, was a 29. Okay, for B, the mean is 516. Sigma, standard deviation's 116. And that student's actual score is 680. So we just plug in the numbers. Okay, so student A finished 1.5 standard deviations above the mean. Student B finished 1.4 standard deviations above the mean. So the best relative score would be for student A. Okay, and that's where we're going to leave off our lesson with question 16. We're going to pick up 17 next week, or this coming week, I should say. And we'll talk about those. Those require a little bit of extra effort, and we'll talk about those as a separate lesson. So have a good day. We'll see you on the next lesson.